In this video, we'll have a look at the exam of January 2021 and we'll solve these 4 questions. As usual, we'll not look at the theoretical part of the question, so this question here is covered by the theoretical course. So here's the first question. Find bases and dimensions for all 4 fundamental subspaces of the matrix that you see on the screen. What is the rank of this matrix, and express the last column of the matrix in terms of the other columns. So try to do this question by yourself and push the pause button. So here's the solution. So as usual, what we do is take the matrix A and we stack an identity matrix next to it, so that when we do elimination at the end here, we have the elimination matrix. So let's start. Well, obviously here the first pivot is 2. In this column we have 0, so we have to produce zeros below the pivot, right? So we can do this using these elementary operations, right? As usual, you take the element that you want to eliminate and you divide by the pivot. So here you have a 3 and here a 5. And if you perform these operations, this is what you obtain. We go to the next line and here we have a pivot -2. We want to create a 0 below the pivot, right? So we have to do this elementary operation. We take this element divided by the pivot, so the multiplier is 2. If you perform this, well, elementary operation, this is what you obtain here. And you see that in the next line we have zeros, so we only have 2 pivots, so the rank of the matrix is indeed 2, right? So to continue our elimination procedure, what we do is create now zeros above the pivot, right? So here the multiplier will be the element to eliminate divided by the pivot, so this is -3 over 2, right? If you do this, this is what you will obtain. So we have our pivots, right? And we have zeros below the pivots and above the pivot. So what we can do now is make sure that the pivots become ones, and we can do this by multiplying the first and the second line by the multipliers that are given over here. And this is what we obtain, right? And it's kind of easy to read from this column here that the 4th column can be written as, well, -1 times the second column plus 2 times this column, and this is what is given over here, right? So for the column space we have to take the corresponding columns corresponding to pivots in the original matrix and multiply by constants, right? So take linear combinations of the corresponding columns in A, columns corresponding to pivots, and this is what you obtain. And you can obtain the left null space from the elimination matrix. This row vector, if you pre-multiply here this matrix by 1 -2 1, you will see that it is producing this 0 vector. You can check this, right? So for instance, we have 2 plus 10, this is because of these 2 ones, -2 times this one, it's 0. And if you continue, you will see that you produce indeed this row of zeros. So if you take the transpose of this one, you obtain, well, a base for the left null space. You can check this because you know that the base vectors of the left null space should be orthogonal to the base vectors of the column space, right? So if you take the scalar product of this vector with this vector, you should have a 0, and this is indeed the case. And if you take the scalar product of this vector with this vector, you should have 0, and this is also the case. So check. We can be confident that these, well, subspaces are indeed correct. What we had to do here for the row space is to take, well, the rows that correspond to pivots. You can do this in, well, the row reduced matrix, the row reduced echelon form, or in the original matrix, and then you take linear combinations, and this is what you obtain. Well, to obtain the null space, what we have to do is to bring this matrix over here in this, well, format over here, where you have an identity matrix, right? This is an identity matrix, and where this matrix is the so-called F matrix. And what we have to do here is to make sure that this first column here is brought at the end over here to obtain this matrix. And we know that for this matrix here, to obtain the base vectors, what we have to do is to construct minus F over an identity matrix, and it's an identity matrix of dimension 2, right? Because we know that this matrix has to have 4 rows. If we do this, this is what we obtain. But of course we have to remember that this is not what we had at the origin, so this one has to be brought here on top. And if you do this, well, you'll have a first column that is this one, a second column that is this one, and then you can take, well, linear combinations, right? Of course, you should check that A times this vector produces a 0 vector, and that A times this vector produces the 0 vector. And if you do this check, you will see that this is indeed the case. Of course, we know that the vectors of the null space are orthogonal to the vectors in the row space, right? So if we take scalar products of this one with this one and this one, we should have 0. And if you take scalar product of this one with these two, or with these two over here, we should have a 0. If you do this check, you will see that this is indeed correct. So this yields the solution for the first question. So here's the second question, and it is, well, to find the values of A for which the system of equations AX is equal to B has no solutions, an infinite number of solutions, and a unique solution. For the values of A for which there is an infinite number of solutions, express this solution in full detail. And there is an additional question that should not be forgotten. Well, what is the null space and the rank of A as a function of A? Let us have a look at the solution of this second question. As usual, what we do is, well, bring the system in augmented form. So this is the A matrix, and we have stacked the B column just right next to it. So what we'll do is Gauss elimination. So we'll create zeros below the pivots so that we can start the discussion. So we have a first pivot over here. We create zeros. So these are the multipliers. By now we should know that you take the element to eliminate divided by the pivot. So this yields a 3 and a 4. This is then what you obtain, right? So we have in the second line a pivot in -7. To create a 0, we need a multiplier of 1. And if you perform this elementary operation, this is what you obtain. So now we are in a position where we can do the discussion. Now we can factorize this polynomial in A as shown over here, and you can see that when A is different from 4 and different from -4, this matrix will be in upper triangular form, and what we can do to find the solution is back substitution, and in any case what you'll have is a unique solution, right? So we'll have to discuss the cases A is equal to 4 and A is equal to -4. If A is equal to -4, you'll have a 0 over here, but this element will be -8, so you'll have an equation of the type 0, well, x3 here is equal to something that is different from 0, so obviously there is no solution. In the case where A is equal to 4, we have an equation of the type, well, 0x1 plus 0x2 plus 0x3 is equal to 0. This is always satisfied, so we have 1 degree of freedom, right? We have an infinite number of solutions. So we see here that the rank of the matrix will be 2 and that we have a null space of dimension 1. So what we do is plug the value of A in this system over here, and what we can do now to find this, well, infinite number of solutions is to continue with Gauss-Jordan elimination. So we have to create a 0 over here. We do this using this elementary operation with a multiplier -2/7, and then to create a pivot of 1, what we can do is multiply the second line by -1/7, and this is what we obtain. So here we have this identity matrix dimension 2, and here we have the F matrix, and here we have this, what we had called in the course dp, right? So now it's very easy to obtain the overall solution in the case where A is equal to 4. You take the particular solution, which is this one over here. This can easily be seen from the system in this format, right? That this is a particular solution, and then you add, well, alpha times a base for the null space, right? So you should check that this is indeed a particular solution and that this is a vector of the null space, right? So we have now answered the first part of the question. Do not forget that there is a second part over here. Not that difficult because we have all the ingredients. When A is different from 4 and different from -4, well, then the rank of the matrix is 3 and the null space is just the 0 vector. When A is equal to 4 or when A is equal to -4, well, we have a matrix of rank 2, right? So obviously the null space will have a dimension 1, right? And notice that if A is equal to 4 or -4, we'll start from the same matrix over here. Okay, so the null space will be the same in the case A is equal to 4 or A is equal to -4, and you can simply obtain it as shown over here. Remember that this is here minus f over an identity matrix here of dimension 1. This is what is generating this base vector. And this concludes the second question. So here's the third question. Find the parabola, and the equation is given that comes closest to the points that are given. There are 5 points, and give the best estimates of the parameters C0, C1 and C2. So as you can imagine, this is a least squares problem. Use the most efficient way to solve the problem, knowing that you'll have to solve the problem again in the future with the same values of t. So what will change in the next problem is that, well, the values of p of t will change. As usual, try to do this by yourself first. Well, let us have a look at this third question. So the first thing that we have to do is to write it in a matrix format, of course. So in general, the points are t1, p1 up to tn, pn. Here n is equal to 5, so up to t5, p5. We have to impose that the parabola goes through each point. So how do you impose this? Well, you say that, for instance, p1, in our case 0, is c0 plus c1 times t1 plus c2 times, well, t1 squared, right? So you can rewrite this in this, well, vector format, and you can see this as, well, a scalar product, right? So here t1 obviously is equal to -2. So you can do this for each coordinate point and you'll end up with 5 equations. So here I've written the fifth equation. p5, 0 is c0 plus c1 t5. It's c1 times 2, right, plus c2 times t5 squared, right? So we'll have here c2 times 4, right? If you combine these 5 equations, this is how you can write this, well, in the general form, right? If you have more points, well, you'll have to add more equations. So if you particularize this to our case, this is the system of equations that you obtain. Obviously there are 5 equations and 3 unknowns, right? So in general there will be no solution, but there will be a solution in the least squares sense, right? What is said over here, that you have to use the most efficient way, knowing that you'll have to solve the problem again, well, with the same times, right? So this means that this matrix A here will stay the same all the time, and what will change is the B vector, right? And if you know this, right, that you have a least squares problem that will always be of the type ax is equal to something that will vary, the most efficient way to work is to use the QR decomposition of the matrix A. So here's the least squares problem that you have to solve. Try to solve it by yourself using this QR decomposition method. So here's the solution. Our matrix A is over here. We need a QR decomposition, so we need to apply the Graham-Schmidt procedure that is outlined in the theoretical course. Notice that, well, you have to keep the first vector, right? And since the second one is orthogonal to this one, if you take the scalar products of those two, you'll have 0. Well, you can keep the second one as well, because you have to subtract its projection on the first vector, but there will be nothing to subtract because they are already orthogonal. So the third vector is obtained as follows. So you take this one and you have to subtract the projection of this one on the previous vectors, right? And if you do this, this is the vector that you obtain. In the QR decomposition, we take A1 bar, A2 bar, A3 bar, and you have to normalize them to give them a unit length, right? So we need now to compute R. We have Q. Well, this is the matrix where we stack Q1, Q2, and Q3. QR is equal to A. We multiply both sides of the equation by Q transpose, and we obtain this equation over here. So this is Q transpose and this is A, and now it's just a matter of computing this, and you should have here a matrix that is upper triangular, and you can see that this is indeed the case. So the original problem that we have to solve is this one. We can write A as QR, and if you take this equation and you multiply on both sides by Q transpose, what you'll have here is a system under this format. Okay, so you'll have Rx, this is X here, this is R, is again Q transpose, and we'll do this in the general case because we know that we might have to solve this problem again, but for different P's over here, P1 up to P5, right? Here we have called them B, right? If you do this computation and you multiply each equation by, well, the first one by square root of 5, the second one by square root of 10, and the third one by square root of 14, well, you can write this system of equation in this format. And now it's crystal clear here that if you have other coordinates but for the same t's, you'll end up with the same system of equations where you'll have to change, well, the independent column over here, right? In our case, this column is simply, well, 70, 0, minus 140, because all components are 0 except B3. B3 is equal to 70. The nice thing about this system of equation is that R is in upper triangular form, so what you can do is back substitution, right? From this equation, the last one, it's clear that C2 is equal to minus 10. From the second equation, you can see that, well, C1 should be equal to 0, and if you plug the solution of C2 in this equation over here, you can see here that this leads to C0 is equal to 34, right? So in this case, the most efficient way to solve this least squares problem is to use the QR decomposition of A. So here's the fourth question. Find the values of A and B for which the matrix A is positive definite. For A equals B is equal to 1, you need to compute two factorizations, and you need to factor A as R transpose R, and you need to do this, well, using the pivots and using the eigenvalues. There's also a question about the use of the concept of positive definiteness in the second part of the course, so state space control methods, and of course, well, this concept comes into play when you talk about LQR control. As usual, try to do this by yourself first. Well, a first condition for this matrix to be positive definite is, of course, that it is symmetric. So this imposes A is equal to B. One of the methods to see that a matrix is positive definite is to look at the upper matrices and to see if the, well, upper determinants are all positive. So this one obviously is, because the determinant is 1. If we take this matrix here and we compute the determinant, we have 2 minus a square. That has to be positive. So a square is smaller than 2. Obviously a square is positive. And if you take the matrix A and compute the determinant, you'll have 6 minus 4a square is positive. So a square is smaller than 3 over 2. A square is again positive as well. So we'll take the most restrictive condition, which is obviously this one. If this one is satisfied, obviously this one is satisfied, and this leads to the following condition on A. So let us now work with A is equal to B is equal to 1. So you obtain this matrix over here, and let us have a look at the first factorization, the one related to the pivots. So what we have to do is to compute the LU decomposition and then the LD L transpose decomposition. So we need to do elimination. We have a first pivot, we need to create zeros below, so we need to perform this elementary row operation with a multiplier, that is 1. This is what you obtain. You go to the next line, you have a new pivot, and you can create a 0 over here doing this elementary operation. And if you do this, well, you have here a matrix that is upper triangular, and that's the matrix U. We have shown in the theoretical course that you can construct very easily L by taking an identity matrix, right, and placing the multipliers at the right spot. This multiplier has been used to create a 0 over here, so we place it here. This one here has been used to create a 0 over here, so we'll place this 1 over here, and everywhere else we put zeros. We have now our A is equal to LU decomposition. What you should do, of course, is check this, multiply L and U to see that you have A. And then you can obtain, since the matrix is obviously symmetric, an LD L transpose decomposition. And here D is a diagonal matrix with the pivots that are on the diagonal. Here you have an additional pivot, which is 2, right? And here we can see that this matrix A is indeed positive definite because the pivots are all positive, right? Using this LD L transpose decomposition, we can obtain an R transpose R factorization of A. We just have to take the, between quotes, square root of this matrix here. This is allowed because the elements are by definition positive, since the matrix is positive definite. So this is the square root of D, right? And we multiply by L transpose. So let us now compute this factorization R transpose R related to the eigenvalues. So we need to compute the eigenvalues and eigenvectors of this matrix with A is equal to B is equal to 1. So we need to compute this determinant. So I won't go over the details of the computation, but this is what you should obtain. As you can see, you have an eigenvalue that is 2, and you have two other eigenvalues, 2 plus minus the square root of 3. A quick check shows that the sum of the eigenvalues is indeed 6, right? And this should be equal to the trace of the matrix, and this is 6 as well. So now what we need to do is compute the eigenvectors, right? Once we have the eigenvalue, we know that an eigenvector is a vector, for instance for lambda 1 here, that is such that a v1 is equal to lambda 1 v1, and you can rewrite this in this fashion. So if you take this matrix over here and you plug lambda 1 is equal to 2, this is the system of equation that you obtain. If you take lambda 2 is equal to 2 plus square root of 3, this is the system of equation that you obtain. And if you take lambda 3 is 2 minus the square root of 3, this is the system of equations that you obtain, right? So for instance, if you in this system of equations fix v13 to 1, the third equation will lead to v12 is equal to minus 1, and the first equation will lead to v11 is equal to minus 1. So this is an eigenvector. For these two it's a bit more difficult, but it's still doable. If you set v23 to 1, the last component, the third equation leads to v22 that is given over here. And what you should do to compute v21 is not use the first equation, right? Because you'll have to divide here by something complicated. It's better to take the second equation and you plug the value of v22 and v23 in here, and very quickly you obtain v21, and this is the eigenvector. You can do the same type of exercise for v3 and this is what you obtain. Of course, we need to normalize those vectors, so you need to divide by the length, and of course this is here a bit complicated, so I've left it like this. You can, well, factorize A as Q lambda Q transpose, with the Q defined as follows: Q1, Q2, Q3, obtained using the eigenvectors and giving them a unit length, right? And once you have this decomposition, well, you can see that R can be obtained as follows. You need to take the square root of lambda, right? This is between quotes, and then you multiply by Q transpose. Obviously, this kind of calculation you can leave it like this. You should not spend your precious time at the exam to do this type of calculation. All I want to see is that you're able to do a computation of the eigenvalues and eigenvectors.